Let's see if we can decode the matrix of the neural netverse. A little bit along the lines of this whole Terrance Howard situation where 1 times 1 is equal to what? 1 times 1 equals what? So there's a big question mark here. Is it equal to 1? Is it equal to 2? Is it equal to 3? Is it equal to something? Well, let's look at this equation that I have right here. It's a little bit powerful equation. N times n equals a bunch of stuff. So we're going to plug in 1 as n, giving it a dimension of 1 dimension, and we have a one-dimensional vector, so we get 1 dimension, boom. We're just going to plug in 1 to this formula. Let's go ahead and do that. So we have 1 times 1 plus 1, and then we're going to divide that by 2, and then we're going to go ahead and add this, put a little circle around here, because these aren't real additions and multiplications, they are tensor operations. Over here we have 1 times 1 minus 1 divided by 2, and if we do the math here, that is going to be equal to 1 plus 0. Huh. So that's the real answer then. I guess it is really just equal to 1. But what is this 0 over here? I mean, there's a bunch of things that I have in mind to do with 0, but for now, we're just going to leave it at that. And we're going to say that we have one symmetric tensor here. And so this is basically going to be a spin 0 singlet. All right, that just means it's a point. This thing over here is the anti-symmetric, but it literally doesn't even exist. So that's just 0. So it just kind of goes away. Now we're going to be left with this next thing. This is 2 times 2. Let's do our times tables. 2 times 2, let's go and plug that into the equation. You get 2, and then a 2 plus 1 divided by 2. And you can add this to the 2 times the 2 minus 1 divided by 2. We're going to get something like, on this left side, we get 6 divided by 2 is 3. And we're going to add that to the right side over here. We should get 1. Okay? And then this is the anti-symmetric version. So over here is the anti-symmetric version. This is the symmetric version. So really what we have here is a spin 1 triplet. Spin 1 triplet. And this is a spin 0 singlet again. All right, very similar things. We sort of popped out with the spin 0 singlet on this side. And then we have a spin 1 triplet over here. And the way that this kind of works is that, I don't know if you've ever seen like spins for the electrons, but they kind of look like this. You can do, let's do this. You can do a 1, 0, do a 1, 1. And so here's your decomp, where we actually have this showing up in quantum mechanics. So you got your spin 1 triplet right here, negative 1, 0, 1. And then you've got a spin 0 singlet over here, which is just a 0, 0. This is how you can kind of pair these up, such that spin is always equal to a certain number. But anyway, we're going to go over to the next level, which is 3 times 3. And why did I say that this is the neural netverse? Because we're basically just going through layers of neural layers here, like stacks. We got a little stack that we're going through. Okay, so then the next level is going to be, we have these crazy theories. You know, you got something like Helix quantum gravity, which counts the closure rules for helixes closing. Yeah, and in fact, this right here is a 1-strand helix. This is a 2-strand helix, and this here is a 3-strand helix. And so we should have closure rules for how these things actually close. And that was sort of what Helix quantum gravity was all about. But the problem is that the 5 by 5 one kind of nullifies the idea a little bit. Not really, actually. We'll have to see how this goes. But here we have a triple helix to make this a little bit nicer. Sure, whatever. So it's getting a little complicated. Here we kind of have maybe the quad helix we were talking about before, where they kind of intersect sort of this angle, maybe. I don't know. It could be. It's still a little bit weird over here. Yeah, the idea is that this is going to be U1, and we'll explain what that means in just a moment. This one is actually SU2. This one is going to be SU3. It's strange because we're switching between different groups, but let's go into the 3 by 3. So we kind of have this whole situation. If we plug this into the formula, 3, and then we get times 4 is 12 divided by 2. It's going to be 6 over here. And then we can go and add that over here. We get a 3 minus 2. Um, it should equal, so what's 3 times 3? 3 times 3 is 9. You should be getting this one over here. This is a little bit complicated, but this is the idea here is that we have quarks come in sixes, or leptons in quarks come in sixes, and over here we have the anti-triplet, and in fact that is going to be RGB, the 3 colors that we could switch between the quarks here. So this kind of gives us the electromagnetic force over here. This one over here gives us the weak force. Weak. This actually gives us the color, which is the strong force. And then 4 by 4, let's go and calculate that one. All right, this is mind-blowing because so far, um, all this stuff, we could maybe laugh at it away. We could laugh it off and say it's just string theory or something, right? But this is where the proof really, really shows up that there's concrete evidence that we really exist in 10 dimensions, right? At least it's some kind of a hint, perhaps, okay? Because here's why. Because 4 times 4 is 16, yeah? And if we decomp it like this, decompose this stuff, we're going to get like 10 on this side, and then we get a 6 over here. And I'm not actually sure whether that's going to be the anti or the not, but the idea here is that we have 10 components of general relativity. So, you know how you get the metric tensor GUV? Well, it turns out that this actually has a massive amount of components. There is 1, 2, 3, 4. You're going to get G1, G01. I don't know, there's a lot of them. 1, 2, 3, 4. Because you're going to have X, TXYZ kind of like this, and then another TXYZ kind of like this. So you have to sort of keep track of everything. And then how they combine together. So you get X, X, Y, Y, Z, Z. Okay, so we actually have 16 components, and what's crazy is that, if I'm not mistaken, these guys over here should cross off, and if we do that, then we can actually, because those should be like the same number, I believe. But if we do that, we're going to get only 10 components remaining. So 1, 2, 3, 1, 2, 3. We're subtracting 6 from the 16 component thing because of symmetries. And so we actually get the whole metric tensor right here with the 10 components of the metric tensor. So we're actually describing gravity with this 4 by 4 right now. And that is actually mind-blowing because, like, again, all the other stuff you could laugh it off, but when you start describing general relativity, general relativity is definitely a real thing. And the other thing here is Lorentz boosts and rotations. So those would be sort of those W matrices or whatever. We can kind of do 3 rotations, 3 boosts, right? And so these are the Lorentz transformations. Holy smokes. Okay, so we're able to get 6 Lorentz transformations and then the 10 components from general relativity, the metric tensor, from the 4 by 4. And that's just very interesting. Okay, so you can see how this is appearing like a neural netverse. Got 4 different layers over here. 1, 2, 3, 4. Now the crazy thing is that this is U1, SU2, SU3. We're kind of going down the groups. You'd expect this to be an SU4, but it's not. It's actually SO13. So I don't know what's going on here, but the idea is that we have different stacks of this neural network and it's sort of like swapping out stacks. So now we're kind of in this layer here, but there's still another layer that we can get into. And this is we kind of took a look at this at the other video a little bit. This is This is SU5, and this is the grand gut theory that they discovered. Let me put this as gravity over here. The grand gut theory that they discovered in 1974. These two guys, Georgi and Glashow, they discovered that you can actually take 15 plus 10, and so that gives you 25. And this anti-10 is really important uh, because there's ways that we could start to essentially calculate quark number charges and all sorts of interesting things there. So let me just do that real quick for fun because I think this is awesome. Essentially, what we'd like to be able to do is we'd like to have a generator. This is a hypercharge generator where the trace is equal to zero. So to zero, we're going to have negative a third, negative a third, negative a third, plus a half, and plus one half. If we do that, um, if we add these all up, they're going to equal zero. All right, and we're in 5 dimensions. So this is pretty sweet. Oh, we got a 5 dimensional thing. Let's realize that we also have the anti-symmetric version of this. So instead of having negatives over here, we have pluses, and then these two are negative. All right, so we're just building this generator, the hypercharge generator, in 5 dimensions, and we've gotten the trace to go away, so it equals zero. And we're going to claim that we could take SU5 and sort of decomp this down into SU3, SU2. So far that makes sense. 3 plus 2 is 5. But we also have a U1 sticking out somewhere. Now where the hell does that come from? Because 3 times 2 is 5. That doesn't make a lot of sense. So let's see if we can take our 5 and like, how do you make a 5? You could take 3 times 1 and then you can add that to 2 times 1. We'll make it 1 times 2 like this. And if we do that, then it should work out a little bit like this, where we can kind of see that there's 3, 1, 2, 3. We'll make a little thing here that says this is the 3's right here. And this right here is also a 2. These things are actually 3 antisymmetric, and these are 2 antisymmetric. Okay? Everything's pretty simple so far. But let's go ahead and take this 3, and let's realize that there is going to be a negative 1/3 charge here. Put that right along with that. And with this 1, 2 right over here, you get 2 of these, and their charge is 1/2. So far, we have actually extracted something that looks like quantum numbers. You have your color triplet, a doublet, a weak singlet, a color triplet, a weak singlet, and a hypercharge. And here you have the color singlet, the weak doublet, and another hypercharge. I don't think that one's the correct one that actually describes our model. We need to take the 5 anti-symmetric. So then we get something that's actually describing our model. We get this anti-3 and a 1. And then the decomp is essentially the same. But over here we have a 1 anti-2. And so now we're just pulling these charges instead. And you can see we're going to get a third. And then we're going to get negative a half. Okay, so it's pretty simple how we can sort of decomp this 5. And we're getting our 3 groups out of this. We've got the color. It's the color right here. This is going to be our doublet, which is the weak. And then this last bit right here, this charge, that is actually the hypercharge Y. So this is the hypercharge. And that's exactly what this is. This is the hypercharge generator. So the hypercharge generator gives us the U1, and then we just have colors and weaks here. All right, this is pretty insane because this is actually deriving the standard model from like fives, when we live in 4 dimensions. And what is this 10 doing here? Well, that's another insanity. Because see how over here, if we look at like this decomp, we have a 10. So there's like 10 components of the metric tensor which are interacting. There's like 10 ways to, well, there's 16 ways to interact if you have 4 dimensions, but only 10 of those are actually unique. So there's 10 ways to interact uniquely with 4 dimensions, and that's kind of what the metric tensor is telling us. So, these internal strands that we have inside of our neural netverse, these strands are kind of implying that there's like more than just the regular old 4 dimensions. There's like internal strands. Okay, but let's just go to the 10 version real quick and try to calculate for 10. Because 10 is very difficult. So for 10, we have to realize that it comes from this Y5 over here. It comes from this Y5. Alright, so this 10 comes from the Y5, and what we have to do is start figuring out what like the math is. You do the 3 times 2. Actually, let's do 3 times 1. I'm going to sort of do this on 2 lines. We're going to start down here. We're going to say that 10 equals 3 times 1 uh, times 1 and 2. So what we're doing is we're kind of combining the triplet and the doublet over here. And since we do that, we're going to take negative a third plus 1/2. And so then we can say that 10 is actually equal to, when we tensor these together, what are we going to get? We're going to get a 3 and a 2. And then we add these charges together, we're going to get a 1/6. Okay? And then the next thing is that we have to take a 3, 1, and take it anti-symmetric with another 3, 1. Alright, and it's anti-symmetric. What we're going to get is something like this, where 3 cross 3 is equal to that 6 plus 3 anti. And we're taking only the anti-symmetric version of this. So we're going to take 3 anti. And then when we do 1 times 1, we also get a trivial 1 out of this. So we'll keep that as sort of the next piece of the 10. And if we wanted to figure out these charges, we're taking 2 of the same, 2 3s. So we're just do negative a third, minus a third, and we're going to get negative 2/3. And finally, we'll do the last one, which is going to be 1, 2, anti-symmetric with another 1, 2, and again, use anti. And these, if you do 2 times 2, you get 3 plus 1 anti. And so we will go ahead and take the 1 anti from this. And we will, oh, wait, it's on the other side. We get 1 anti on the 2's are on the right side here, the 3's are on the left side there, so we'll go ahead and stick the 1 along with the 2's. It doesn't really matter there, but we're doing, because 1 and anti-1 are exactly the same thing, so it's actually possible that this might be an anti-1 as well, but I don't really know. But anyway, over here we're going to do 1/2 plus 1/2, because we're taking 2 of the same, and we're just getting a charge of plus 1 over here. So there we go. We've actually derived here all the different quarks and leptons and fermions and stuff, I believe, from the standard model. They should be generally familiar numbers. Right, color triplet, weak doublet, and the hypercharge of 1/6. Like, this should be very familiar right here. Alright, and so this is how, like, they were able to come up with this theory Georgi and Glashow in 1974, they popped up with this thing and they were like, holy smokes, like this gives us all the charges, all the particle fermions, like what, like it actually does. And so that is why it's just like shocking. This SU5 can really give us what we want, but it doesn't really describe everything because remember that there's this issue with like proton decay and stuff like that, and some extra gauge bosons that we're not really supposed to have. So maybe this is a little too much. Maybe the neural network, and I was thinking to myself, it could be that this is like the conformal field theory, where you sort of break apart your layer here, and you've got your sort of your fourth layer here, which is they have this thing called ADS4, CFT5. It could be some sort of a duality going on here. We have a four-dimensional thing here, and the CFT on the outside. But this is in fact the neural netverse. You see, it's exactly the same as a neural network where you have neurons at each layer. And in fact, I think a neuron would literally be the same thing as saying how many dimensions do you have at each layer? You got one neuron in this layer, two neurons in that layer, three in this layer, or it could be the gauge bosons that come out of this because I know that this one, if you look at the dimensions here, the dimension of this thing is going to be, let's look at our groups. The dimension of U1 is actually just one. So the dimension here is one. It turns out that you have one generator in the U1 group, okay, in electromagnetism. And then if you go to SU2, then you do SUN dimensions is n squared minus 1. And so you actually get three dimensions over here. And so this gives us the three generators of the SU2 group. That's the Pauli matrices. Okay? Pauli matrices are going to be the same three. And then if we go into SU3, we have a dimension of n squared minus 1. That is going to be dimension 8. And again, that gives us the 8 generators, which are actually the gluons. All right. And then once we go into this one, the pattern kind of stops there. So, yeah, this is very, very interesting. And hopefully this was helpful and starts to unlock the theory of everything in terms of the neural netverse, in terms of these helixes. These are different theories that we're sort of looking at here. And they're all sort of pointing to the same thing that, maybe string theory and unit theory, they got a point. Like, we can't just describe things with a 4x4. We have to expand this a little bit further and see what are things come out of this. I'm pretty sure that if we get a neural netverse equation and how we can sort of stack these layers together, we might need a smaller structure than what we thought. String theory might be a little too much. I think the neural netverse has a better chance of perhaps being able to describe all this stuff with one equation because it's all here. 1, 2, 3, 4. It's like doing your times tables. Anyways, thank